All right, welcome back. So we're going to finish off this topic on set theory by talking about some kind of advanced probability topics pertaining to conditional probability as well as random variables and expected values. Now, again, if you've never heard of these topics, it's okay. We're going to stop. We're going to start from the very bottom and we're going to work our way up. But first, you have to understand the basics of probability. So that's what we did in the last few examples. So again, please make sure you've reviewed those examples before moving on. But before we move on to those advanced topics, I just want to very quickly talk about some properties of probability that you probably have figured out already, but I'm going to write them officially anyways. So firstly, if you remember this equation that we had, E complement is equal to S minus the size of E. So sorry, the size of E complement is equal to the size of S minus the size of E. So essentially, if we want to know, how many events or how many objects are in an event or not in an event, they are directly related to the sample size, the size of the sample. So if we're looking for the probability of complement of E, so what is the probability that E doesn't happen? Well, this is equal to 1 minus the probability that E does happen. And I hope you understand how this comes to be, because if you take a look at this equation, the size of E complement is like this, and then we're going to divide it by the sample size. So that is the probability of E complement. And 1, we can write it as size of S over size of S, and then minus the probability that event E happens is going to be the size of E minus the size of S. Now, if you take a look at our equation up here, what is the complement of E, the size of the complement of E? Well, we can plug in S minus E for this part. So size of S minus the size of E over S. And now I hope you can see that the left-hand side and the right-hand side are exactly the same. So anyways, the only thing that I want you to take out of this is that this is a property of probability. So just make sure you understand that part. There is one other property of probability that I want to make note of before we move on to something a little bit different. And that is that if I wanted to find the probability of two events happening, or one event or the other happening, so here is the equation. So if I take the probability of E1 or E2, this is equal to the probability of E1 plus the probability of E2 minus the probability of E1 and E2. So that is to say that the inclusion exclusion function that we talked about before, it works with probability as well. So you can see that the reason why this would work is because the S, the sample size, the size of S is constant in this equation. So you see how here, if you take a look at this equation that we had, we can actually split the 7 factorial over 2 factorial over 2 factorial into each of the individual denominators. Okay, so that is going to correspond to the probability of E plus the probability of T minus the probability of both. Okay, so I hope you can see where that's going, but just to let you know that this is a thing, this is another property of probability, so just please take note of that. I'm not going to do an official proof here, but I think everyone through mathematics can kind of see that that this must be true. Okay, but the important thing that I want to talk about here is conditional probability. So oftentimes we want to find out the probability of something happening, but we know we have knowledge beforehand that something else that's related to this thing has already happened. So in such a case, we say that event A is what we're after, right? We want to know what the probability of event A is, but we know that event B has already happened. And furthermore, event A depends on event B. Okay, so event A depends on event B, and we know that B has already happened. So in this case, we call this a conditional probability because once again, it is that we are looking for an event A to happen, but we already have the foreknowledge that B has happened, and B directly relates to A. So here's the official definition. Let A and B be events with the probability of B greater than zero, the conditional probability of A given B. Okay, so the event that A happens, the probability that event A happens, given that B has happened, is denoted by A and then straight line B. Okay, so this is the conditional probability straight line. So it is equal to P probability of A and B divided by the probability of just B happening. All right, so we'll put this equation into practice in 1 second, but let's take a look at an example. Suppose we flip a coin 3 times. What is the probability of getting an odd number of tails given that the first throw is a tails? Okay, so I want to know the event, right? The event is the odd number of tails. Now, the first thing we'll do is we'll label this as A because that is what we're after. And given that the first throw is tails. So I'm going to call this B. Now, before we apply this equation, let's just see what the answer is. Okay, so you're told that you're going to throw the coin 3 times. So the first thing that you know is that the first throw is tails. Okay, so what are the possibilities given that the first throw is tails? Well, it could be that the rest are heads. It could be that you have one head and one tails, or it could be all tails. All right. So what is the probability that you have an odd number of tails? Well, in this case, you have one tail in all three throws, so that's an odd number, so that's odd. In the last case, you have all three tails, which is also odd, but notice that in the other cases, they're even number of tails, so that's not what we're looking for. So clearly the answer here is 2/4 or 1/2. Okay, so the answer is 1/2. Now, where does this 1/2 come from? Well, let's apply the equation and see where this 1/2 is coming from. So first, we want to find the probability of A given B. The equation that we're given is probability of A and B over the probability of just B. All right, so what is the well, let's start at the bottom here. What is the probability of B happening? Okay, so I'm going to continue writing out all of the cases. So these are 4 of the cases, but if we were just to say how many outcomes can happen with 3 coin flips? Well, we don't only have to analyze the heads, we have to analyze the tails as well. So what if the first one was sorry, I had that backwards. We don't only have to analyze our the tails being first, we also have to analyze the head being first. So if heads was thrown first, we again have 4 cases. Okay, and head, tail, tail. Now, in fact, I've listed out here all 8 cases. Okay, so these are all 8 cases of what would happen if I threw 3 coins. All right, so what the probability of B is the size of B divided by the size of S. Now here, clearly, the size of S is equal to 8. Now where this 8 comes from is that if I make 3 throws of the coin, each throw has 2 possibilities. So the answer here is 2 to the 3. So our S is 2 to the 3. This is our sample size. This is our universe. All right, what about B? So the B says the first throw is a tails. So how many of these have the first throw being tails? Well, this is the one with the on the left-hand side column, and there's 4 of them. And in fact, the equation is 2 to the 2 because if we fill the first box with a tail, the rest of the two boxes each have two choices, so 2 to the 2. Okay, what about A and B? Now, A and B, the size of A and B over the size of S is the probability of A and B. So what is A and B? Well, it is that we get an odd number of tails and the first row is a tails. Okay, so we get an odd number of tails and the first row is a tails. So which one is it? Well, it's this one and it's this one. Okay, so there's two possibilities. Okay, we get an odd number of tails and the first row is a tails. And then what is S? S is again 8. So it's 2 to the 3. So essentially we have 2 over 8 divided by 4 over 8. And you can do a little bit of math here and you can confirm that this is in fact 1/2. Okay, so the probability here is 1 over 2. All right, so this is basically how we do conditional probability. We have to solve an extra problem. So the thing that I want you to be very clear on is that whenever I say, give me the probability of this given this, right? A given B, we have to make sure that B actually plays a role in A. Okay, so most of the problems that you'll see in this course, that is actually the case, but we do have to ask that question of ourselves, right? So does A actually depend on B? Okay, so that's the only way that we can use this equation. All right, let's do one more just to make sure that we understand the idea. So what is the probability that a bit string of length 4 contains at least two consecutive zeros given? Now, anytime I have something like this, I'm just going to label this. So I'm going to label this thing A, given that the first bit is a 0. So I'm going to label that B. So here it seems like we're doing conditional probability again because B does impact A. Okay, it does impact A. So if I have a bit string of length 4, what is the probability that I have at least two consecutive zeros and given that the first bit is equal to 0? So let's analyze here. So I'm going to start with the size of S. Okay, so we're going to need the size of S. So the size of S is here, 2 to the 4, because we're talking about bit strings of length 4, right? So all the possibilities is 2 to the 4. So if you think about 4 digits, each digit has has two ways to fill it, 0 or 1. So altogether, we have 16 bit strings of length 4. Okay, so what about B? What about the size of B? So the size of B here, actually, let me just list out what B is. So B looks something like this. It's the case where it begins with the 0. So one case would be 0, 0, 0, 0. Okay, another one would be 0, 0, 0, 1, 0, 0, 1, 0, and so on. Okay, the question is, how many of these are there? Well, because the bit string of length 4 starts with a 0, there must be 3 digits left. Each of those 3 remaining digits has two ways to fill it, either a 0 or a 1. So the answer here, the size of B, is going to be 2 to the 3. Okay, so please verify this. We have a 0 at the beginning. We know that. We have 3 extra slots, 2 to the 3. Okay, what about A and B? Now I'm filling out all of these things. I hope you know where I'm going with this. But what about A and B? So A and B is answering the question at least two consecutive zeros and the first bit starts with a 0. So now I think we can list out everything here. So A and B will contain 0, 0, 0, 0. So that's one of them. 0, 0, 0, 1 is definitely another. 0, 0, 1, 0, 0, 0, 1, 1, and 0, 1, 0, 0. So I think those are all of them. So correct me if I'm wrong. The size of A intersect B looks like it is 5. Okay, so I've listed them out. We could actually use a counting strategy to solve this, but I think this is easier just to list everything out. And now we want to find out what the probability is of A given B. Okay, so this is the probability of A and B happening over the probability of just B happening. Okay, well, now we can just fill in everything. So the probability of A and B happening is 5 over 8. The probability of just B happening is going to be, I'm sorry, not 8, 16. Of B happening would be 8 over 16. Okay, so the answer here is 5 over 8. Okay, so again, conditional probability, we need to make sure, we need to convince ourselves that A really does depend on B. And in this case, it does. Okay, all right, so moving on. Oftentimes, we are confronted with problems that where we need to assign some value to some experiment or to some experiment outcome. So, for example, let's say that when I flip the coin 3 times, I want to assign a function, we'll call it x of t, that is talking about how many heads are observed when I make the flip. So t is the outcome. Okay, so I want to just figure out how many heads are observed through these 3 flips. So this is what's called a random variable. So we can assign a value to an outcome of an experiment. So for example, we might have another problem that says, what is the probability that 4 ones will be generated when 5 bits are generated randomly? Right. So this type of problem requires a random variable. And once again, a random variable is an assignment of an outcome to a number. Okay, so it's an assignment of an outcome to a number. So let me show you what I mean by this. Now, in our example, suppose a coin is flipped 3 times with outcome t, and I want to let x of t be the number of heads that are observed. Now, remember, t is an outcome. So, for example, if I see the outcome as let's see here. I actually wrote down all of the outcomes. So if I have heads, 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 okay, so I flip 3 times and it comes out heads, heads, heads. The value that I'm going to assign to this outcome is going to be 3. All right, there are other outcomes. So x, let's say, is of heads, heads, tails, is going to be the same as x of heads, tails, heads, which is the same as x of tails, heads, heads. Am I missing anything here? I think that's all. This is equal to 2, right? So in all of these outcomes, the heads happens 2 times, so they're equal to 2. Uh, and then there's another case where the heads only happens once, so HTT is equal to THT and TTH. And this is equal to 1. So all 3 of these outcomes of flipping the coin 3 times, there's only 1 head. So these are cases where it's assigned to be 1. And then finally, there's one last case where we have the tails. So the x of these tails is going to be 0, okay, because there are no heads that are present. Now you can see here that there are different values that I can assign to outcomes. Now, one question that I can come up with from this is, if I flip a coin 3 times, what would I expect to see as an x, right? So most of the time, what would I expect to see as my result for x? And there's a calculation here because it does depend on the probability. And we're going to see that in 1 second. But let me give you another example of a random variable, and then we'll move on to what I just said. All right. So suppose a pair of dice is rolled with the outcome I followed by j. Okay, so there really shouldn't be a bracket here. I mean, this should actually be a round bracket because there is kind of order associated with these with this throw. So let xij be the total of the numbers that are rolled. So I roll the dice 2 times. I roll it first and then second, and I add up the 2 numbers. So xij is going to represent the total for the numbers that are rolled. So for example, if I roll a 1 and then I roll another 1, then that is going to be equal to 2. That value that I'm going to assign to that outcome is going to be equal to 2. Okay, so again, remember what random variables are doing are assigning outcomes to numbers. Okay, assign an outcome to a number. Okay, here you see that if I roll a one and then followed by two or vice versa, then the answer here is three. The answer here would be four. The answer here would be five, six, seven, eight, 9, 10, 11, and 12. All right. So another question that I can answer here is if I throw a pair of dice, what would be an expected value? What would I expect to see most of the time when I roll this dice, right? So what would, sorry, what, let me say that again. What would I expect as a total of these two dice when I roll them? Okay, so in order to answer those two questions that I just proposed, we're going to need what's called an expected value. Okay, so expected value means that I have a random variable associated with some result, okay, with some outcome. I want to figure out what the expected value would be when I do this experiment over and over again. Okay, so what is the expected value of the coin flips? Okay, so it turns out that the expected value has the following definition. So the expected value of x is that for all the outcomes, for all the different outcomes in the sample space, I'm going to take the probability of s happening multiplied by the value of x. Okay, now remember, this is our random variable x, and it again takes an outcome and assigns a value to it. Whatever the probability of that outcome being, I'm going to multiply it to the value. Okay, I'm going to sum them all up, and ultimately that is going to be the result. That is going to be the expected value of the random variable. Okay, so let me show you an example. Suppose a coin is flipped three times with the outcome t, and let x of t be the total number of heads observed. Okay, so this is something that we've done as a random variable earlier. What is the expected value of x? So here, we're going to take the sum of all the probabilities along with the expected values. Now, I just want to go back very quickly and take a look at this example. So we essentially have four outcomes, four numbers that can be represented by this random variable. Now, in total, there are 8 cases. There are 8 outcomes that can occur, right? Ranging from heads, 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 all the way down to tails, tails, tails. So according to the equation of expected value, I'm going to multiply the probability of each of those cases happening multiplied by the expected value. So you notice that here we have heads, 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 which gives a value of 3. So this is a probability of 1 over 8. Okay, so one case over 8. So I'm just going to write this out. So we have 1 over 8 multiplied by the value 3. So the probability of that happening multiplied by the value. Okay, what about the value 2? I take a look at the value 2. I have 3 cases. All 3 of these cases give the value 2. So it's 3 over 8. So I'm going to do plus 3 over 8 times 2. And then the third one, you can look back at the slides, is also 3 over 8. I'm going to multiply that by 1. That is the value of the 1 for that random variable. And then I'm going to add 1/8 times 0. Now, if I add all of these together, this should give me 3 over 2. Okay, so the expected value, now notice the expected value is not one of the outcomes for the random variable. However, it is an average of what I would expect to see when I flip flip a coin 3 times. Okay, so the expected value of x in this case would be 3 over 2. All right, let's take a look at our other example. So again, suppose a pair of dice is rolled with the outcome ij. Let xij be the total of the numbers rolled. What is the expected value of x? Now, again, we're going to do exactly the same thing. Take take the value of the random variable and multiply it by the probability that it will happen. So again, I'm just going to take a look at this chart. All right, so if you take a look at total outcomes here, we're rolling two dice, right? So we're rolling a pair of dice, and we're assuming order here. We're assuming we're throwing the first dice and then throwing the second dice. We have six outcomes for the first throw, and we also have six outcomes for the second throw. So it's six squared, which is 36. So in total, we have 36 different outcomes, and each of these values are shown here. So I'm just going to take the numbers and I'm going to take the probabilities associated with those numbers. So I'm going to start with 2. And again, you can refer back to this slide, but I'm just going to list out what I have here. So I have the value 2 has the probability. So let's start with the probability. The probability of 1 over 36 times 2, right? So you see that the sum, when the sum sums to 2, there's only 1 out of the 36 cases. There's 2 out of the 36 cases that will sum to 3. There will then be 3 out of the 36 cases that sum to 4, and then 4 out of the 36 cases that sum to 5, and then so on. So 5 out of 36 times 6, and then 6 out of 36 times 7. So 7 out of 38 times 8. I'm sorry, not 7. 5 over 36 times 8, and then 4 over 36 times 9, 3 over 36 times 10, and then 2 out of 36 times 11 plus 1 out of 36 times 12. Okay, so anyways, I think you understand where I'm going with this. So I take the probability of each case and then multiply it by the value of the random variable. And if I total them, that is going to be the expected value. Now, you can see that there is a really even distribution here. If you work out this equation, you actually get the number 7. Okay, so just verify my work here, but you do get the variable 7. So what is the expected value that you will get given that I throw a pair of dice? The sum of this pair of dice is going to be 7. Okay, it's going to be expected to be 7. Okay, so that's basically how random variables work. Now, you might be saying that these two examples are actually quite simple. They're quite straightforward, and it does make a lot of sense. But when you get into something a little bit more difficult, so there are some applications that get a little bit more difficult that we are going to use random variables and expected values. I'm not going to give you any more difficult examples in this course, but just know that if you go on in statistics or you go on in computer science, you're going to see many examples of random variables being used to estimate either running time or an expected value of some experiment. So this is actually very useful, a very useful tool for those areas. Okay, so what I'm going to do is I'll stop the video here for now, and we're going to move on to our next topic. So we're done with set theory. Again, please go back and review this video, and please make sure that you understand everything that's taught here. There is going to be an in-class as I will give throughout the semester. So have a look at the in-class and make sure that you understand how to do those questions in the in-class as well. So I will see you in the next video.